Hi, I'm going to show you 3 important proofs involving right triangles. The first is Pythagorean theorem. Pythagorean theorem states that the sum of the squares of the legs of a right triangle is equal to the square of the length of the hypotenuse. More simply put, a squared plus b squared equals c squared, where a and b are the legs of the triangle, and c is the hypotenuse. In a right triangle, the hypotenuse is always the side opposite the right angle. There are actually over 200 different proofs to prove Pythagorean theorem. In this one, I've drawn a square and drawn another quadrilateral inside the square. The quadrilateral has 4 congruent segments with length of c. On the outside, we've labeled these lengths of these segments AB, 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 and AB. The area of this large square is one of the sides squared. The length of this side is a plus b. So a plus b, the quantity squared, is the area. Expanded, it's a squared plus 2ab plus b squared, because it is a perfect square trinomial. Now, the area of this triangle is 1/2 AB. The area of all 4 of them is 2AB. So the area of this quadrilateral is a squared plus 2ab plus b squared minus 2ab, which equals a squared plus b squared. Now we prove that this quadrilateral is a square. In a right triangle, or in any triangle, the sum of the angles equals 180. In this case, this angle equals 90. So the sum of these 2 angles has to add up to 90. That means that these two angles, and these 2 angles also add up to 90. Here you see that this angle and this angle are complementary, meaning they add up to 90. These 3 angles are supplementary, meaning they add up to 180. So 180 minus 90 equals 90, showing that this is a right angle. We can show that the others are right angles in the same way. To prove that this is a square, we've already shown that these 4 sides are congruent. To show that they're parallel, you use the theorem: if a line is perpendicular to both of 2 lines, then those 2 lines are parallel. So these 2 are parallel, and we show that the other 2 are parallel in the same way. Therefore, this is a square. The area of a square, as I've said before, is side squared. In this case, c squared. Another way we've already shown the area of this square is a squared plus b squared. So, a squared plus b squared equals c squared. And we've proven Pythagorean theorem. Next, the next proof I'll show you is one involving a right triangle whose 2 other angles are both 45 degrees. We call this the 45 degree, 45 degree, 90 degree triangle. The ratios of the lengths is easy to prove. First off, we know that this is an isosceles right triangle by the converse of the isosceles triangle theorem, because these two are both 45 degrees. Let's call this length x. Now, to find the length of the hypotenuse, we simply use Pythagorean theorem. And we get this length of x root 2. The way these lengths are set up are extremely useful on tests like the SATs. It is also handy to know. Finally, we'll prove another theorem finding side lengths in a triangle whose angles are 30 degrees, 60 degrees, and 90 degrees. For this, we start off by drawing an equilateral triangle. We also know this triangle is equilateral by the isosceles triangle theorem. And we know that these angles all have measures of 60 degrees, because the angles in a triangle, interior angles in a triangle, add up to 180 degrees. Next, what we have to do is draw an altitude. Erase this. Because it's an isosceles triangle, it bisects this angle and bisects this segment. Let's call the lengths of the equilateral triangle 2x. When we bisect it, this length is x. Now, by the triangle angle sum theorem, 60 degrees, 90 degrees, 150 degrees. Subtract that from 180, and we get these angles to have a measure of 30 degrees. And now, to find the last side, we use Pythagorean theorem. Oops. And we have this with a length of x root 3. And that is the relationship of the side lengths in a 30, 60, 90 triangle. Those are 3 proofs involving right triangles. The first is Pythagorean theorem. Pythagorean theorem states that the sum of the squares of the lengths of the legs of a right triangle is equal to the square of the length of the hypotenuse. More simply put, a squared plus b squared equals c squared, where a and b are the legs of the triangle, and c is the hypotenuse. In a right triangle, the hypotenuse is always the side opposite the right angle. There are actually over 200 different proofs to prove Pythagorean theorem. In this one, I've drawn a square and drawn another quadrilateral inside the square. The quadrilateral has 4 congruent segments with length of c. On the outside, we've labeled these lengths of these segments AB, 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 and AB. What we have to do is prove that the area of this quadrilateral, c squared, stop.